example,
Hocam kamera kaldı.
kamera, tamam, pardon. Let's say a head is the linear map given by this rule. Let's say x, y, z is equal to 3x minus y plus 2z minus y plus 5z and then x plus y minus 2z. Okay. So what is the determinant of this? So what we should do, I pick up a basic for R3. So I can just pick up my basic as this vectors. You can pick up any basic. And then we just compute these vectors, images of these vectors on the F. So 1, 0, 0, 1, 0, 0, just 3, 0, and 1. A hex is just 0, 1, 0. So minus 1, 1. And a hex is 3. So 0, 0, 1. So 2, 5, and minus 2. Okay. So what is a hex cube? E1, E2, E3 then? It is just a hex E1 wedge, a hex E2 wedge, a hex E3. So it is the wedge of these three vectors. Okay. So 3, 0, 1, wedge minus 1, minus 1, 1, wedge 2, 5, minus 2. Actually, to make computation easier, it is better to write these vectors like this ones using the basis. So this is just 3E1 plus E3. This is just minus E1 minus E2 plus E3. Which this is just 2E1 plus 5E2 minus 2E3. And then we just take the determinant. We just compute the product. Here I have E1 term. So if I start with this term, then I cannot take this one. I can take either this one or this one. Suppose I take this one, then I have to take the E3 term. So I will have what? 3 times minus 1 times minus 2. So it is 6 times E1, E2, E3. So it is just, so let me just write this one more time. So it is just, the first one is just 3 times minus 1 minus 2. So 6 times E1 into E3. So 6 times E1 into E3. And then I take again this one, but this time I take this guy, and then I need to take this one. So 3 times minus 1 minus 3 plus 5 times 5 minus 15. Pardon, evet bu hocam. 3 çarpı 1 çarpı bu 15 tane E1, E3, E2. So it is 15 times E1, E3, E2 So if I interchange, şöyle yazayım olmazsa E1, E2, E3 artı ne dedik? 15 tane E1, E3, E2. What else? Bu bitti değil mi? Bununla her şeyi yaptım. E3 term'i var. Bunu aldıktan sonra bunu alabilirim. Eksi 1. Ondan sonra da bunu alabilirim. Eksi 5. E3. E1. E2. Başka ne var? Bunu aldım. Ondan sonra bunu alabilirim. Ve bunu alabilirim. 1, eksi 1, eksi 2. Eksi 2 tane. E3, E2, E1. Değil mi? Başka da yok. Right? There are two terms starting with E1 and two terms starting with E3. That's it. And then, so, if I want to write all of them in this form, so what will be the coefficients? So 6 from here. To bring this one to this form, I have to just switch this two. So I have to pick up a minus sign. What about this one? This has to jump twice. So the sign will not change, minus 5. And then here, this has to jump twice, and then this two has to switch. So 3 transpositions, so sign should change. Okay, so the determinant is just 8 minus 20, so minus 12. E1, E2, E3. Therefore, determinant of a head is just minus 12. Okay. Tamam mı? Şöyle de yapabilirdiniz tabii. The matrix representation of a head in the spaces is what? So according to the definition of a head matrix representation, so these are just these will be the columns, right? So 3, 0, 1, 3, 0, 1, minus 1, minus 1, 1, and 2, 5, minus 2. So this is just the determinant of, so minus 12 is just the determinant of this matrix also. Tamam mı? Trace'ini start etmiştik. Do you remember? Evet. If you have an operator, you write it in a basis, and then you just take the sum of the diagonal entries. That's one definition. Or, so if you have an operator, let's say, and suppose you have a basis for V, then you write down the matrix representation of this operator in the spaces, and trace of a head is just, so if this matrix is just Aij, sum of the diagonal entries, so it is A1, 1, A2, 2, A and N. If your matrix, operator is given as in tensor form. So like this. Suppose your operator is like this. So VI capture I stars I from 1 up to 2. So VI is in V, Fi star is in V star. Right? Then trace becomes something very nice. Trace of a head. Of course, it will be this expression if you write this in a basis, but if it is given in this form, it is also equal to the following sum. You know, these are vectors, these are covectors. So these are objects which eats vectors and gives us scalars. So what you do, you just feed each covector with this vector, you get the scalar and add them up. So to the power. Okay. This is equal to this scalar. What is it? Oh. Okay. Last time we also talked about, I guess, Cramer's rule. What was it? Suppose we have a matrix equation like this, a system of equations, and suppose A is invertible. In other words, the term of A is not 0. Then we know that this system has a unique solution, right? Unique solution. We can write down the solution using determinants. That's called Cramer's rule. And how it works? It works as follows. Okay, so let's take a basis. So suppose here A is an, this is an n by n system. Suppose A is an n by n matrix. Okay. What you do is the following. Şöyle yapıyorduk. Şimdi AX equals B can be written like this, right? So this is just, if I write columns of A like this, let's say, okay, V1, V2, Vn, and here I have x1, x2, xn, and here I have v1, v2, vn. When you multiply this out, this is what you get. So first column is always multiplied the first, this entry, right? So when you open this up, this is what you get. X1 times the first column, x2 times the second column, and xn times the nth column is equal to this b. Okay. So B is a linear combination of the columns of the matrix A, and these coefficients are just actually the entries of the solution vector. And then we do the following. Well, okay. We know the following. Determinant of a head is nothing but the determinant of the matrix Aij, right? And that is nothing but actually just the wedge of these vectors. So it is yani şöyle diyebilirim. Bu ve potansiyel eşit daha doğrusu şöyle diyeyim. If you just take wedge of these vectors, you just get determinant of a head times, let's say E1 up to En. Okay. Here, EI is just this column, let's say 0, 0, 1. So you have 1 in the ith place. Okay. So determinant of A is just this expression. Şuraya tekrar edeyim mi? Now, here, in this product, wedge product, let me just replace the ith vector with the vector B. Okay. So instead of ith column, let me just write B here. Let's see what we get. I have V1 up to Vi minus 1. And for the ith column, I have the following. B. B is what? It is x1 times V1, right? B was here. B is this one. B is just x1 times V1, x2 times V2, xn times Vn. So let me just write it down here. X2, V2, xn, Vn, and then I continue Vi plus 1 up to Vn. Okay, now here you see, I have V1 here. So when I open this up, I have V1, V2, Vi minus 1, and then another V1. V1 times V1 will give us 0. Therefore, when I open this up, this term will give me 0. So I can just neglect it. Okay. What about this one? Here I have V2, wedge product, V2, so that will be 0. The only term that will survive is this one. Here I have somewhere xi vi. Right? There is no vi here. There is no vi here. That's why this term will survive, but all others will be 0. So when you put this up, you will get just this. V1, Vi minus 1, and then only this term will survive. Xi, Vi, and then here I have Vi plus 1 and Vi. Tamam mı? Olmadı. Şimdi burada D1 var ya, D1 ile D1'in veci 0. Orada mı sıkıntı var? Yani bir vektörü kendisiyle veç yaparsanız o 0 oluyor. Çünkü o bir yerde determinantta 2 tane satırın aynı olması demek, aynı şey. Ya da n boyutlu bir kutunuz var ama 2 tane kenarı aynı. Yani bir tane dikdörtgeniniz var ama 2 kenarı aynı. 2 kenarı aynıysa dikdörtgen bu. Değil mi? Bunun da alanı 0. O yüzden 0. 2 tane kenarı aynıysa o n boyutlu nesnenin n boyutlu hacmi otomatikman 0'a gelir. So, if I have V1 here, well, since I have V1 here, when I take this product of this with this term will give me 0 because I have V1 with V1. Okay? So this will contribute nothing, therefore I can erase it. Similarly, I can erase this one. Up to where? Up to ith term because I don't hear Vi. So this ith term, xi vi will survive, but anything before that will vanish. And anything after that will vanish because I have here I plus 1 up to n. So the only term that will survive among this expression is the ith term. Therefore, this thing is equal to this thing. I erase all of the terms except this one. Tamam mı? And then here I have this coefficient xi. From the properties of exterior product, I can just take this coefficient in front of this expression. So I have xi times v1 dash v2 dash vi minus 1 vi vn. Okay. So what we see is that you see this thing is what? This is nothing but the determinant A hat times equation, right? So this thing is just determinant A hat. And then just this term, E1 match E1. What about this one? Well, except this term B, it is the same as this one, right? So it is like determinant of A hat. The only difference is that instead of the ith column, you have the matrix, so you have the column B, right? So this is just the determinant of this matrix. You have V1 V2, but instead of the ith column, you have the vector V. So, and then of course, E1 up to En. So we have the following. Determinant of V1, V2, here I have V, Vn, so this is the ith place, times V1 up to En is equal to xi times determinant of a hat times E1 up to En. Now this is a non-zero vector, and I have called it, therefore the coefficient of this non-zero vectors must be the same. One coefficient is this guy, the other coefficient is just this guy. Therefore, we have what? We have the following. Xi is just equal to this determinant. So, determinant of V1, V2, B, Vn divided by determinant of A hat, which is just determinant of V1, V2, Vi, Vn. So you have the matrix A, you take its determinant, and here you just replace the ith column with the column B. You take this determinant, and the ratio of these numbers is xi, the ith coordinate of the solution vector. Okay? So that's the Kramer rule. Lisede görmüştük yani, değil mi Kramer? Bu
Maalesef.
benim görmediniz. Maddesi yok mu? Ben bir tek cümleni gördüm.
Ama bunlar ilk sene büyük olan
Efendim?
böyle maddesi böyle. Bir sene falan.
Tamam. Okey. Şimdi geçen dönem eigenvalue ve eigenvektörü de tarif ettiydim. Bir kısmınız biliyor, bir kısmınız bilmiyor. O yüzden tekrar tarif edeyim. Let evet. Be an operator. So, a linear map between a vector space and itself is called always an operator, okay? It's a linear map, but if the domain and target space are the same, we call it an operator. So, let A be an operator. If B is a non-zero vector, so that's important, non-zero vector, so that A hat B is equal to lambda times B for some scalar lambda, then B is called an eigenvector, and lambda is called the corresponding eigenvalue. So what's an eigenvector? It's a vector so that a head acts on it as if acts on it as scalar multiplication. It just sends this vector to a scalar multiple of that vector. Okay. In general, action of an operator on a vector is something very complicated. Okay. This vector and its image are usually totally different objects. But there are some vectors so that on those vectors, a head acts like, just scalar multiplication. Sends this vector to 2 times that vector. If it is the case, then we say that this is an eigenvector and it's an eigenvalue, corresponding eigenvalue. Okay? Now, if if V has a basis, which is V1 up to Vn, consisting of eigenvectors, then we say that a head is diagonalizable. Why is that? Well, it is because of the following. Since these are eigenvectors, so A Vi is just some scalar times Vi. Of course, depending on the vector, this scalar may change, but sometimes different eigenvectors may correspond to the same eigenvalue. Okay. So this lambda i's are not necessarily distinct real number, distinct scalars. So, okay. And what is the matrix representation of this operator in the spaces? So what will be the ith column or first column? A V1 is just a head V1 is just 1. Lambda 1 times V1, and then there is no V2, 0 times V2, 0 times Vn. So the first column is just lambda 1, 0, 0, 0. What about a head V2? Well, it is lambda 2 V2. So it is just 0 times V1 plus lambda 2 times V2 and then 0 times Vn. So the column here, second column is 0, lambda 2, 0. And it will just continue like this. And the last column will be just 0, 0, 0 up to Vn. Therefore, we have just diagonal entries consisting of the eigenvalues, and all other entries are 0. And of course, in this case, a head has a very simple form. It just sends this basis elements to their multiples. That's why this is a very nice operator. It's easy to compute. And that's why it is called diagonalizable, because in this basis, the matrix is diagonal. Tamam mı? And in this case, of course, we can, for example, write down the determinant. What is the determinant? You may continue, compute it any way you like. But it will be just right to the product of the lambdas. Lambda 1, lambda 2, lambda. If you want, we can just compute it this way. So since this is the base, it's the basis. So I need to compute a head and in the basis V1, V1. So what is this? This is just a head V1, which a head V2, which a head Vn. But what is this? This is just lambda 1 times V1, which lambda 2 times V2, which lambda n times Vn. I know that I can take this constants in front of the product. So I will have just lambda 1 times lambda 2 times lambda n, and then V1, which V2, which Vn. So this element is mapped to just this multiple times itself. Therefore, this multiple here is just our determinant of a hat. Evet.
Olabilmesi için lambdaların birbirinden farklı veya lambdaların aynı olması durumunda farklı vektörlere denk gelmesi zorunlu.
Bir daha söyle.
Şöyle, lambdalar birbirinden farklı olduğunda okey, sıkıntı yok.
Aynıysa
Aynıysa onların görüntü vektörleri, eigen vektörlerin birbirinden farklı olması gerekiyor.
ben onların hepsini şöyle diyelim, bir yerde şey yaptım, hani kabul etmiş oldum. Bunun basis olduğunu kabul ettim ya. Öbür türlü senin söylediğin gibi fark etmek lazım. O kısma daha hiç girmedim. How can we represent anything as a tensor? Well, it sends the I to lambda I, the I from 1 up to n. So I can just write ahead like this then. So if this is the basis V1 up to Vn, this is the basis for V. We consider the dual basis V1 star, Vn star, basis for the dual space, and write this gadget here. Vi cancel Vi star I from 1 up to n. So when you feed this guy with Vi, this will give you 1, and then you have lambda I times Vi. Okay. What about the trace of A? Well, by definition, trace was what? You just feed this vector to this covector and then add them up. So this is just I from 1 to n, Vi star, lambda I, Vi, but lambda I goes out, Vi star, Vi. We know that it is just 1. Therefore, this is just sum of lambda i's. Of course, that's not a surprise, right? The place of this operator is just sum of the diagonal entries. Peki. Şimdi arkadaşlar söyleyecek şeyden biraz ondan bahsedelim. Aygen radyoların değil mi? Aynı olması durumunda işler karışıyor. Şöyle bir şey fark edeceğiz. Tahtayı değiştireyim. So let lambda be an eigen value for an operator Since this is an eigenvalue, there is some eigenvector, right? So that that vector applied to A hat applied to that vector is just lambda times that change. We define a subspace corresponding to this eigenvalue. Let W lambda be the subspace of B consisting defined by şöyle tarif edeyim. Bu lambdaya karşılık gelen bir subspace. Neden oluşacak? Eigenvektörlerden oluşacak. Yani şunlardan. Evet. V is equal to lambda B. So I consider all the vectors so that a hat applied to that vector is just lambda times that vector. These are not all of them are eigenvectors. Why is it? Because zero vector satisfies this equality, right? A hat times zero is just zero, but zero is never an eigenvector. So this is this is a vector space. It has zero elements, but except the zero element, all the other vectors are non-zero, therefore they are eigenvectors. So they are eigenvectors of A hat corresponding to this eigenvalue plus the zero vector. This is a subspace. Here I said it's a subspace, but this needs a proof, of course. Why it's a subspace? Proof. You have to prove two things, right? For this to be a subspace, it should be closed under vector addition and scalar multiplication. So let's say V1 and V2 in this figure, and C is a constant. We want to show the following. We must show the following. V1 plus C times V2 is in this figure, right? Bunun burada olması ne demek? Tanımı. Buna E hat vurduğum zaman bunun lambda katını bulmam lazım. Let's check. E hat V1 plus C V2. Well, since A hat is linear, this is just A hat V1 plus C times A hat V2. But V1 and V2 are vectors in this set, therefore they obey this rule. So this is just lambda times V1 plus C times lambda times V2. I can take this gadget into lambda parentheses, so I have this. And what we have seen is that a hat applied to this vector is just lambda times vector. Therefore, V1 plus 3 into is number. Therefore, it's a subspace. Good. Okay. Right. So let me start this here. So next time I'll talk about again something we discussed last semester, Van der Monte matrix, and then I'll show that eigenvectors corresponding to different eigenvalues are linearly independent. And then we will pass to diagonalization.